Hi, today we're going to move on with a little bit more about the circular kinematic equations, the rotational ones we've been discussing in the last few videos, and we're going to connect them more with our linear kinematics that we've been covering for the majority of the semester. So just to recap, for linear kinematic equations, uh, we had three kinematic equations of constant acceleration, and they were these. And then, so that was our position kinematic equation or velocity kinematic equation. And then if we put those together, we got this third one here. So we had one, two, and three. And we could eliminate time using one and two, and we would come up with three. The last video or so, we looked at rotational kinematics or angular kinematics, where we had these three equations, and they kind of mapped one to one, right? We had three equations that were very identical in form, really, and they were these. Where we had an angular position equation, an angular velocity equation, and then if we took those two equations and eliminated the time from them, we got this third one that was a combination of those two. But exactly the same thing, except for we use this sort of new definition of angular position, um, and angular velocity. And so if we had some XY coordinate system that looked like this, but we had an object that was traveling in some circular path that went around like this, and we were at some position along that path, we could describe this using, an x and a y vector in two dimensions, or to make it sort of easier, we could describe it based knowing the r of that circular path, we could describe it just given that angle or the angular position, right? And what we're going to discuss today is, this linear type of motion, these linear kinematic equations are describing how this object would move in straight lines, and we would use vectors and break it up into components and such. And this rotational kinematic equations are describing the exact same object moving in a circle using just this angular position and angular velocity. They must be connected in some way. So today we're going to briefly discuss that connection and how we can go back and forth. And it all boils down to essentially the unit radians, really, right? So if we are moving along this circle and we've moved some distance up that path, that distance we could define as some arc length s along that path. And we know the radius r of that circular path. We define the unit of angular position as just the ratio of that arc length to the radius of the circle. Or written another way, that arc length, the position along that circular path, is equal to r theta. So immediately, we can kind of go back and forth, and we could use trig and such to get x and y components for that. But this is sort of the core thing that's going to let us go between velocity and angular velocity and such. And one way we realize that is if we're looking at this vector, the velocity vector at that point, it's going to have a tangential component vt. That it's going to have some speed along that tangential direction as it goes around that circle, right? And that velocity, that vt that we're looking for, is just how fast that position along that arc length is changing. So it's the time derivative of this distance along that arc length. And since we know what that is in terms of our angular sort of coordinate system, we can just substitute that in and we get the derivative of r times theta. But since we're moving along that circular path, r is constant, this just ends up being d theta dt, or r omega. So we have our first way of connecting um, our sort of linear description of motion. We can get that tangential speed, how fast it's moving in meters per second along that circular path, is just related to r times omega, how fast that angle is changing. So that's the first one. And now if we wanted to know that tangential acceleration, say it's speeding up or slowing down, how fast it's moving around that circle, it's going to have some tangential acceleration, which is just going to be how fast the speed in that tangential direction is changing. And we can do the same sort of thing, just substitute what we now know our tangential speed is in there. And again, the radius along that circle is constant, so this is just d omega dt. And this gives us another way of connecting it. We have this tangential acceleration is going to be equal to r times alpha, our angular acceleration. So essentially, what we're seeing here is if we want to go from sort of a tangential coordinate system, our position along that circular path, we take the angular position and multiply it by the radius. Likewise, if we want the tangential speed, we take the position, the angular angular velocity, and multiply it by the radius of the path. And then likewise for acceleration. And so now, if we go all the way back up here, we have our kinematic equations for angular description of motion and our kinematic equations for a linear description of motion. And we can sort of take these, whatever the problem sort of it might have a more convenient way of describing it or one we're more comfortable with, we can describe the kinematics using those equations and that, and then go down to these sort of three equations and connect tangential speeds and accelerations and positions with our angular positions. And we're almost done. There's one other thing we need to know, and it comes back to how we first started the sort of motivation for doing all of this, right? If you recall, we had an object going along a circular path like this. If this object was moving here, and it can be, we're not in uniform circular motion, we're just some type of circular motion, it's going to have some acceleration, right? And if you recall, we could separate that acceleration into a tangential acceleration. That was pretty sloppy arrow, sorry about that. Let me try that again. Where we had some acceleration in the tangential direction that's describing whether that velocity vector is getting larger or smaller in magnitude. Is it speeding up or slowing down? But because I'm turning as well, it's got some radial component of acceleration, something that's describing that velocity vector changing direction. This was one of the whole motivations of developing this angular description of motion. Is there a way we can connect this to our angular description of motion? And it turns out there is. The textbook goes through a nice sort of derivation where they do vector addition and subtraction in the visual representation where they use arrows in that. It's kind of involved. Another way is a little more complicated using some calculus and unit vectors. But for today, I think it's enough to just qualitatively describe what it is, right? If you imagine a circle, right? If you're going really fast, if you have a large VT, large tangential speed, you're going to have to turn sharper. You're going to have to turn harder, right? Or you're going to have a larger um, uh, tangent or radial acceleration, right? Likewise, if that circle is really small, if you're turning around a very sharp corner, right? So if you have a small radius that you're traveling along, that's also going to have a large radial acceleration. You're going to have to turn sharper to do that. So you have this intuitively, you probably or can kind of get behind that there's going to be this proportionality where the faster you're moving, you're going to need a larger radial acceleration to describe that motion. The smaller the circle it is, and it turns out what the actual equation for that is that tangential speed squared divided by the radius is how we quantitatively can calculate the magnitude of that radial acceleration. Also, this is frequently called centripetal acceleration, which just means center seeking. It is an acceleration that's always pointed towards the center of that turn or the center of that circle, and its magnitude is that tangential speed squared divided by r. And with that, we're done. We can connect both our linear descriptions of motion, where we're giving in units of meters per second or meters per second squared or whatever, and our radial or angular description of motion. The one thing that we have to remember when we do this, though, is these equations all started from this sort of definition, which has to be in units of radians, right? If you give that angle in units of degrees, this doesn't work. None of these will make sense. So to make the kind of connection between angular and linear kinematics, we need to have that angular unit be in units of radians. But that's the gist of it. Now we're able to uh, like I say, describe the motion using whichever set of equations are more comfortable or more convenient for that problem. And then, depending on what's asked, if you need to go back and forth, we can use these sort of four equations that connect them, provided our angular description of motion is in radians. So that's essentially it. That's all the stuff in the first section of the course with kinematics. We'll meet in our synchronous sessions to go over this some more, probably do some examples. If you have questions, don't hesitate to call or email or reach out.